In this video, I'd like to talk about the math question of the day for Sunday, July 2nd, 2023. And with this problem, we need to determine if this series converges or diverges. And determining whether series converge or diverge is typically taught in a Calculus 2 class. So at this point, go ahead and pause the video, see if you can work through this on your own. And when you're ready, unpause the video and we can go through this together. Now, assuming that you have attempted the problem, let's start working through this. And with this series, you may be able to notice that this can be rewritten as a geometric series. And of course, that might not be completely obvious, but the main idea is that we have 3 raised to the n power, and 2 is raised to the minus 3n power. It's also raised to the first power, and 3 is also raised to the second power. But ignoring that, just focusing on the variable terms, we have 3 raised to a positive n and 2 raised to a negative n. And that's a clue that we can end up with some type of ratio, let's say k over m, raised to maybe the nth power. And if we can rewrite it like this, then we could have a geometric series which are more straightforward to interpret than many types of series. In fact, if our common ratio, this k over n, we could actually just call this r. If this common ratio r is less than 1 or bigger than negative 1, not equal to those, then we can actually add this series up and find an answer. So let's try to manipulate this into a geometric series so that we can follow that strategy. And what we can do is rewrite each of these expressions here, these factors, with exponent properties. Since we know when we're adding exponents or subtracting that we can split this up into a product of 2 different exponential expressions. For instance, 3 to the 2 plus n, we can rewrite this as 3 squared multiplied by 3 to the n. Since if they have the same base, you can just add the exponents. Likewise, 2 to the 1 minus 3n, we can rewrite as 2 to the first multiplied by 2 to the minus 3n. And let's now rewrite our series here. We have an infinite series. So we'll take the sum as n goes from 0 to infinity. We have 3 squared multiplied by 3 to the n, multiplied by 2 to the first, multiplied by 2 to the minus 3n. And we can combine the 3 squared and the 2. This is just 9, and times 2 makes it 18. So we have the sum here as n goes from 0 to infinity of 18 multiplied by 3 to the n. And we'll put the 2 to the minus 3n in the denominator as 2 to the positive 3n. And from here, since we want both of the exponents to be the same to rewrite this as a geometric series, we can use exponent properties again. Since we know that when we have an exponent to an exponent, that the exponents multiply. Or if we go in reverse, if we have multiplication, we can write this as an exponent to an exponent. And of course, we know that 2 to the third power is just 8. So this can be rewritten as 8 to the n. And rewriting our series here from n is 0 to infinity of 18 multiplied by 3 to the n over 8 to the n. And if we have a quotient and they're both raised to the same exponent, we can rewrite that as that quotient raised to that exponent. So if that wasn't clear, we had 3 to the n over 8 to the n. Since they're both raised to the nth power, we can just rewrite this as 3 over 8 to the nth power. So we've manipulated this series so that now it is a geometric series. And this right here, this is our common ratio. We can call this r if we want. And this is our starting value, which is typically referred to as a when you look at a formula for this. And since r is less than 1, this will actually converge, which technically answers our question. We just wanted to know if it converged or diverged, but let's actually add this up. Since geometric series, in terms of series, are relatively straightforward. So let me actually make a little bit more room here. We'll leave in the a and the r. Let's say that we have some general infinite geometric series. We have a, that's our starting value, plus a times r. Since remember, in a geometric sequence or series, going from one term to the next, we multiply by the common ratio. So we multiply again by that common ratio. Now we have a times r squared. We do it again, and we do it infinitely many times. The next term would be a times r to the fourth, and so on. If we call this infinite sum s, we can rewrite a new sum where we take this sum here and multiply it by the common ratio. So we can multiply s by r, and essentially that r just distributes to everything. We get a times r here, a r squared here, a r cubed here, and so on. Now, the trick to find s, to actually add that up, is to take this top sum and subtract this bottom one, this new one where we multiplied s by r. We take s and we subtract r times by s, and notice what happens. From this top sum we have an a, but we don't have a down here, so we're not losing that. But every other term will cancel out. We have ar minus ar squared minus ar squared, ar cubed minus ar cubed, and so on. Every single term going out to infinity will cancel, and we get this nice equation, which we can now solve for s. Let's factor an s out from this left-hand side. We get 1 minus r, this is equal to a, and we divide by 1 minus r, so that s is a over 1 minus r. And we know what a is, that's 18. We know what r is, that's 3/8. So let's actually plug those in. We get 18 up top and 1 minus 3/8 down below. And this is really 8 over 8 minus 3/8, which simplifies to 5/8 in our denominator. And if I make a little bit more room here, this sum here is 18 divided by 5/8, or multiplied by 8 over 5. And 18 times 8, we can do 10 times 8, that's 80, plus 8 times 8, which is 64. 80 plus 64 is 144, and all of that is divided by 5. So not only did we find that this series here converges, we can actually show that this is just equal to 144 over 5.